So this is an example of an acid-catalyzed hydration. Acid-catalyzed hydration. So hydration, just like if you stay hydrated, if you hydrate a molecule, you're adding H2O. So you're adding an H and an OH, that's your H2O. And then how you're going to do that is going to involve a proton transfer. So a catalyst is a molecule that makes a reaction happen faster, but doesn't really get used up itself. By the end of the reaction, you have just as much of it as you started with, but it speeds the reaction up. And as you can see, acids and bases are very common things that do that because they do proton transfers, which change the stability of things. So by changing stability, you can make things more reactive and therefore react faster. And so you can sort of hit the gas pedal, make a reaction happen faster. To use this term, you can catalyze the reaction you want to happen, often by adding an acid or a base. And in this particular reaction, you add an acid. So because of that, there are two different ways you might see this. You could either see it as H2O, that's the water, and H2SO4, that's the catalyst, the acid that's going to be used to catalyze the reaction, to change the stability of stuff. But the truth is when you put sulfuric acid, that's what H2SO4 is, when you put that into water, it gives its H's away. It gives away its H pluses, and ultimately that turns into H3O plus, and then SO4 2 minus. And so the real acid you tend to work with is H3O plus. And so you can see both of these sort of recipes for acid-catalyzed hydration. So on the reaction list that you might see online, you can see H2O, H2SO4. Here you're seeing H3O plus. And so you'll want to know that those are conceptually the same thing. Those are both the same reaction, acid-catalyzed hydration. Okay. This mechanism is actually very, very similar to hydrohalogenation. If you were to draw this H3O plus out, hydronium, it's an oxygen with 3 hydrogens on it. Anytime oxygen has 3 bonds, it has a full positive charge. And if you were to draw this out, you can see that that molecule is actually very, very similar to the molecule we used a moment ago in hydrohalogenation, because the chlorine was really something that let that H plus go. It's sort of a leaving group that leaves the hydrogen. And this H3O plus is almost the same thing, except what the leaving group is happens to be different. So it's still going to leave that hydrogen behind, but that sort of leaving group is now this H2O plus molecule. And so the mechanism is going to follow the mechanism for hydrohalogenation very, very closely. The only difference is that the leaving group is going to be different. And then later, when that group attacks as a nucleophile, it will be a neutral nucleophile rather than a full negative nucleophile. So we'll have just one extra proton transfer at the end. So that's abstractly what it's like. Let's draw it out, and hopefully it'll be more concrete, make a little more sense. So we'll take this molecule, and just like we did with hydrohalogenation, anytime you see two molecules and you're unsure about how they may react, whether it's in this class or in a future class, remember 95% of reactions happen because opposite charges attract. And so if you're ever unsure how molecules might interact, start by identifying the nucleophiles, the place where you have negative charge, and the electrophiles, the places where you have positive charge. So you have a nucleophile anywhere where you have full negative charge, partial negative charge, a lone pair, or a pi bond. You have electrophiles anywhere where you have full positive charge, partial positive charge. If it were me, I wouldn't just stare at the molecules waiting for these to pop out at you. I would start by choosing one molecule and then working your way through each of these tables. So for example, in the carbon chain on the left, we don't have a full negative charge, we don't have a partial negative charge because we don't have atoms with very extreme electronegativities. We don't have a lone pair, but we do have a pi bond, and so that pi bond is going to be our nucleophile. So you're thinking of that as a conceptual unit. Notice this is the same as when we discussed hydrohalogenation, the mechanism for that. That pi bond can always act as a nucleophile, no matter what weird molecule it happens to be on. Let's stay on this carbon chain. We don't have any full positive charges. We don't have any partial positive charges. And so as a conceptual unit, even though we may have never seen this molecule before, we know exactly how it's going to react. It's going to react as a nucleophile. Now, if we go to the other molecule, hydronium, excuse me, we can play the same game. There are no full negative charges on it. There are no partial negative charges on it. There is a lone pair, it happens to be on the oxygen here. So that lone pair might, theoretically, be attracted to an electrophile. The only thing is the oxygen already has a positive charge, so if it gets close to an electrophile, that positive charge is going to push or repel that electrophile away. So it's not going to be a very good nucleophile there. And we don't have any pi bonds. For electrophiles, we do have a full positive charge on the oxygen. And then we also do have some partial positive charges on those hydrogens. Now, if you were just reasoning through it, you might be tempted to think that, okay, we know that this pi bond is going to be our nucleophile. What do nucleophiles do? They attack electrophiles. And you might be tempted to think that it would attack the oxygen. The only thing is that oxygen has 8 valence electrons right now. Right? It has 2, 4, 6, 8 valence electrons. It has a full octet. So if you're going to form a new bond to it, one of the bonds that it has to break. And hydrogen is a terrible leaving group, because if hydrogen tries to take the electrons holding it onto the molecule and leave, it becomes what's called a hydride, which is a hydrogen with a lone pair and a full negative charge. And because hydrogen is so small, that negative charge is stuffed into such a small space, it's extremely unstable. Right? Stable means spread out. Unstable means not spread out. And here you have a charge that is not spread out at all. So hydrogen is a terrible leaving group because if it tries to leave, it becomes extremely unstable. And so although there is a strong electrophile in the middle of this molecule, because there's no leaving group, it's very, very hard to form a bond to it. So instead, the electrophiles that are attacked are the ones on the outside, the slight positive hydrogens. And so that's what our nucleophile attacks. It attacks one of those hydrogens there. And notice this first step is the same first step that occurred in hydrohalogenation. It's a proton transfer. It's going to change the stability of that carbon chain. It's going to make it a little more reactive. This is actually our catalyst here. This is our acid catalyst. Now hydrogen can only form one bond. So if it's going to form this new bond, the bond that it has is going to break. The electrons will go to the most electronegative place nearby, which is that oxygen there. So there's our proton transfer. Looks very, very similar to hydrohalogenation. And when you're redrawing the products, you keep everything the same unless it's touched by a curved arrow. So this bond won't be here anymore. It'll form a lone pair on that oxygen. That's going to put out that positive charge fire that was there. And here, this is a Markov-Nikov addition, and if that means that the hydrogen is going to go to the less substituted carbon, so that the more substituted carbon is the one that has the carbocation, the positive charge on it. So we sort of walked through the different possibilities for this in the video for the hydrohalogenation mechanism. That nucleophile was on both of these carbons. So which carbon does the hydrogen add to? It adds to the less substituted carbon in this case, because you want the more substituted carbon to have the positive charge. That's where the carbocation is more stable. So this again is Markov-Nikov addition. Now, anytime you have a carbocation, you have to ask yourself, will it rearrange? And in this case, you would sort of analyze that by looking at what type of carbon the positive charge is on. This carbon is bonded to 2 other carbons, so it is secondary. To the right, this carbon is just bonded to one other carbon, right? Notice this is a hydrogen, so it's only bonded to one other carbon, so that's primary. And to the left, this carbon is bonded to 1, 2, 3 other carbons, so that is tertiary. In other words, we have a more stable position for the positive charge to be on to the left of where it is now. And that means that we're going to have a carbocation rearrangement. So anytime you have a carbocation, you always have to check for rearrangement. So here, whenever you know you have a carbocation rearrangement, you go to that more substituted carbon, you focus on that, and you look at the smallest thing that's there. It's the smallest thing that's going to move. And the smallest thing is usually a hydrogen. If it's there, there is a hydrogen here, so you'd want to draw that hydrogen in. And the curved arrow shows the movement of electrons. So it always has to start at either a bond or a lone pair. So you'll start the tail of that curved arrow at the bond of the thing that's moving, the hydrogen, and the head will point at the atom that has the positive charge. So that's our carbocation rearrangement. So let's redraw the molecule that we have left after that. And in this case, everything stays exactly the same except for the things that are touching that curved arrow. So the hydrogen's going to move over. It brings its electrons with it. And so now this positive charge isn't here anymore. Instead, it's at the place that is now missing those electrons, that more substituted, more stable tertiary position. So after that carbocation rearrangement, we have a more stable carbocation, a tertiary carbocation, rather than a secondary one. Now, I'm going to clean this up just a little bit. I'm going to erase these hydrogens because they are really there, but they're implied in these skeletal structures. So you'd want to see them with your mind rather than with your eye. You draw the hydrogens anytime you need them for a mechanism. So for example, we had to draw the hydrogen here in this last step because otherwise there's no way for us to show it rearranging. But once it has rearranged, you don't have to draw it again because it's not participating in the mechanism anymore. It's implied in the skeletal structure, so it doesn't need to be drawn explicitly. So at this point, we've done if you sort of look back, get a bird's eye view of what we've done the proton transfer, which is always going to happen as the first step. We've done the carbocation rearrangement, which will happen only when there's a more stable position right next door. And so now these two molecules are sort of left in a room. The carbon chain, you want to think of it as a conceptual unit. And in this case, because it has a positive charge, this is going to be our electrophile. And so we need to look for a nucleophile on the other molecule, and that's going to be the oxygen that has both a partial negative charge and lone pairs. So in this next step, that nucleophile is going to attack the electrophile, and so that's going to be nucleophilic attack. And that's going to add that water molecule onto the carbon chain. So here, those lone pairs will attack this carbon. That'll be our nucleophilic attack. And we'll redraw everything. Only things that are going to change are the things touched by those curved arrows. So in this case, we can attach that oxygen onto that carbon there. And here. Now, anytime oxygen has 3 bonds, it has a full positive charge. So this oxygen has a full charge there. That is something that's visually small but conceptually huge. That full positive charge is telling you that this is not your final product. This is still reactive. 95% of reactions happen because opposite charges attract, and this has a full charge. And so we have to change the stability of this. We have to hit the brakes. We have to make this stop reacting. And in fact, we should have seen this sort of need to do a proton transfer to change the stability of this. We should have seen that coming. especially if you remember the mechanism for an SN1 reaction. You might remember from that mechanism for an SN1 reaction that if you had a nucleophile that had no formal charges, so it didn't have a full negative charge, then you had to do a proton transfer in the last step of that SN1 mechanism. And so here we had a nucleophile, water, that had no formal charges. It had partial charges, but no full formal charges. And so now, after it is attached, it has a formal charge, and we have to get rid of it by doing that proton transfer at the end. So we're going to use another water molecule, and you might ask, where is this water molecule coming from? Remember that when we draw molecules, we're really drawing populations. It might look like an individual molecule that we're drawing, but those individual drawings represent huge populations. Every time you exhale, you breathe out more atoms than there are stars in our galaxy. And so where is the water coming from? It's coming from this beaker full of trillions upon trillions upon trillions of water molecules that are there. We don't draw them if they don't affect the carbon chain, but when they do start to affect the carbon chain, like here, we will draw them. So this water molecule, those lone pairs there, are like little nucleophiles. The oxygen has a slight negative charge, and so it can steal one of these hydrogens. The hydrogen can only form one bond, so if it's going to form that new bond, the bond it has to break, and the electrons will go to the most electronegative place nearby. In this case, that's on that oxygen. And so you are left with two molecules here. So this oxygen now won't have that negative charge because it gets those extra electrons. And this hydrogen will be attached to this water molecule. That oxygen now has 3 bonds, and therefore a full positive charge. And those are your 2 products. So if you think back to where we started, what we ultimately accomplished is we added a hydrogen, and that's still there, though you'd have to see it with your mind rather than with your eye because it's implied on the skeletal structure, and we added an OH. In other words, we added an H and an OH, or we added water, H and OH. And so that's why this is called a hydration. The other thing you might notice is that we started with an H3O+, and we ended with an H3O+. That didn't get used up in the reaction. We needed that to make the reaction happen, but the amount of OH in the beaker at the beginning and at the end of the reaction is going to be the same. And so something you use to make the reaction happen faster, but that doesn't get used up, is called a catalyst. And in this case, the catalyst is an acid, so it's acid-catalyzed hydration. So in acid-catalyzed hydration, you'll always have proton transfer as your first step. You may have rearrangement depending on what the molecule is, if there's a more stable position for the carbocation to be nearby. You'll always have nucleophilic attack, and you'll always have a proton transfer at the end. So hopefully you can see the similarities between this and hydrohalogenation.